Okay, hi everyone. This is the last QCrypt session. The topic is post-quantum security, and we'll have, as usual, 3 talks back to back, and at the end we'll have a time for a Q&A. If you're interested, if you have any questions, feel free to type them now as we speak, and please mention to who the question is addressed, since we have multiple speakers. And we'll start with Yeledon. I hope I pronounce your name correctly. The floor is yours.
Thanks. Can you see my screen? Yes, thanks for the introduction. And this talk is about the Measure and Reprogram Technique 2.0, multi-round Fiat-Shamir, and more. And this is joint work with Haar and Christian Mayans. Our work is about proving Fiat-Shamir digital signatures, and in general, Fiat-Shamir zero-knowledge proof systems secure against quantum attackers. Where by secure, we mean secure in the quantum random oracle model. We extend the existing QROM technique by Don, Veer, Mayans, and Schaffner to a larger class of applications, notably multi-round Fiat-Shamir signatures, bullet proofs, and sequential OR proofs. And finally, we also show that the security reductions that we get from applying this technique are essentially tight. While our result concerns a general QROM technique, I'll start by explaining the main motivating example, namely multi-round Fiat-Shamir. There exists something called the 2n+1 round public coin interactive proof systems. These are a subclass of the zero-knowledge proof systems that Alex talked about, with a constant or logarithmic number of rounds, where a prover can prove its knowledge of some secret key to a verifier by sending a sequence of messages, the so-called commitments, upon which the verifier replies with a uniformly random challenge, and the prover sends the next commitment, etc., until he gets to the final response. But if we want to apply this protocol in a digital signature scheme, we need it to be non-interactive. In other words, we need the prover to send all of its messages in one go. And while now the prover no longer receives these random challenges from the verifier, he will have to compute them himself by taking the hash of each commitment using some publicly known hash function H. And publicly known so that also the verifier has access to it and can recompute these challenges and then check some verification predicate with respect to the sent commitments, the response, and the challenges produced by H. Now to prove security, or more precisely to show that this non-interactive scheme is as secure as the interactive one, we turn to the quantum random oracle model, where we model this public hash function H as an external random oracle to which all parties have quantum query access, which means that the function cannot be computed locally. So the adversary has to send these queries to the external oracle, but they can consist of a superposition of inputs. So when A makes a query, he actually sends a quantum state over to the oracle. Now, in many also classical random oracle model proofs, what we want to do is show the existence of a simulator that can simulate the oracle to the adversary, but also observe the queries. It might be that the simulator needs to know in which hash inputs the adversary is interested. But of course, observing a quantum state may cause it to collapse, and this may influence the behavior of the adversary, so that we can no longer, in general, predict what the output of the adversary will be, even though the simulator might need this output in the security reduction. But then comes our result on the multi-input reprogrammability of the QROM, which says that if we have this scenario where there is some adversary making Q quantum queries to a random oracle, before producing an array consisting of n different hash inputs and some additional output Z, such that some arbitrary predicate V holds of this Z, these X's and the corresponding hash values, then indeed there exists such a simulator which can pick n of the adversary's queries at random, measure them, and then upon the inputs that were found in the measurements, reprogram the oracle to some fresh random values theta. And it will then still produce some output x bar z bar, such that the same predicate v holds of this x bar z bar, but now with respect to the fresh random values theta. And this is for any particular choice of hash inputs x naught. And all of this at a loss at most order q to the power 2n. Now this technique is exactly what we need to prove that the advantage of the best adversary against the Fiat-Shamir transformed non-interactive scheme is at most order q to the power 2n times bigger than the advantage of the best adversary against the interactive scheme, which is what we needed for security. Thank you.
Thanks. We'll have a question at the very end. Our next speaker is Omri. The floor is yours.
Thank you all. I'm just sharing my screen. Okay. Okay, welcome everyone to this QCrypt talk on post-quantum zero knowledge in constant rounds. This is joint work with Nir Bitansky. So in this work, we are going to focus on the construction of a post-quantum zero knowledge protocol. So let's start with defining what exactly is a zero knowledge protocol. This is an interactive protocol between a prover and a verifier. We have an NP language L, and the prover would like to prove to the verifier that some instance X is in the language. Now, the first property of the formal definition is completeness, that asserts that if the instance is indeed in the language and both parties are ran honestly, then the verifier is going to accept. The second property is soundness, that says that if the instance is not in the language, then it doesn't matter what the prover is going to do, the verifier is still going to reject this false proof. And the zero knowledge says that a malicious verifier that tries to learn something interacting with the honest prover, it's going to learn nothing from the interaction. This is formally captured by the following definition. So there exists some polynomial time simulator such that for every polynomial time algorithm implementing the verifier, the output of the verifier at the end of the interaction, which captures everything that the verifier learned, is going to be indistinguishable, computationally indistinguishable from what the simulator is going to output. Of course, the simulator is not going to interact with the prover. So essentially, everything that the verifier learned, it could have just run the simulator and learned it by itself. So more specifically, this work is going to focus on zero knowledge against quantum attacks. That formally means that when protocols are run honestly, they are still classical algorithms, both prover and verifier, and completeness is perfect. If the instance in the language, the verifier is going to accept. Soundness is going to hold against polynomial time quantum provers, and zero knowledge is going to hold against polynomial time quantum verifiers, which means that now this polynomial time algorithm implementing the simulator is going to be a quantum algorithm, such that for every polynomial time quantum verifier, the now quantum state of the verifier at the end of the interaction is going to be efficiently simulatable by this quantum simulator. So what we know in terms of round complexity versus security type, whether it is classical or quantum, we know for quite some time how to do classical zero knowledge in constant rounds since the end of the 80s. And we don't know yet how to do quantum zero knowledge in constant rounds. And a small note is that this question was open even if we let the honest parties be quantum. So the results that we show in this work is that if we assume the existence of quantum fully homomorphic encryption, which is fully homomorphic encryption that can evaluate quantum circuits, and we assume also the hardness of LWE for quantum algorithms, we have a constant round post-quantum zero-knowledge argument for NP. We also have what we call a quantum extractable classical commitment, and these two theorems together, combined with the previous work on zero-knowledge for QMA, it implies the constant round zero-knowledge quantum arguments for QMA. And one thing to say is that this work focuses more on the NP result. So, few words on the main challenges of constructing a post-quantum zero-knowledge protocol in constant rounds for NP. And the main problem is the no-cloning theorem. So let's see why. So recall, how do we show zero knowledge? We need to show the existence of a polynomial time quantum simulator. And one more thing to recall is that the verifier is an interactive machine, which means that it has this inner memory that it keeps to itself, where it keeps tracks of all of the interaction and keeps all of its secrets. And this inner state plays a key role in the simulation. So in the classical world, traditional simulators are black box in the sense that they treat, we recall the simulator has access to the circuit of the verifier, but actually traditional simulator use this circuit of the verifier as an oracle. They treat it as an input-output function. They don't actually use the fact that they hold the circuit. And they are based entirely on the ability to clone this inner state of the verifier. Now, when we move to the quantum setting, this verifier is a quantum computer. Its inner memory is characterized by a quantum state, and we cannot just arbitrarily copy the quantum states that is the inner state of the verifier. And this is the problem with traditional simulation techniques, but more advanced kind of simulation techniques are called non-black box, starting with the work of Barak that actually treats the verifier as a circuit. It doesn't just use it as an oracle. It does more clever things, and it is a great question to ask. What about non-black box techniques? Are they useful to simulate without cloning? To simulate and show post-quantum zero knowledge. And unfortunately, they didn't work because one example is maybe they don't treat the verifier as an oracle, they do more clever stuff, but they still clone the inner state of the verifier one way or the other. And some of them, it's not clear that the quantum analog of these simulators would use cloning, but they definitely use tools that are not known for quantum computations. One example is universal arguments. And the question that we try to answer in this work, can we use the fact that a simulator holds the circuit of the verifier to perform this zero-knowledge simulation in constant rounds without cloning anything whatsoever? And the answer that we gave is that this is possible, and I won't have time to get into the techniques, so thank you very much for listening.
Thanks, Omri. Okay, so for our last talk, we'll have Chris.
Okay. Hi. Can you see my screen? Oh, good. Okay. Thanks for joining the last session of QCrypt 2020. This expository talk is about efficient simulation of random quantum states and random unitaries, and this is joint work with Gorian Alagic and Alexander Russell. Here's an overview over our results. We study the simulation of random quantum objects, so random quantum states and random unitary operations. And in this context, we develop a theory of stateful simulation. So we simulate an oracle, but we do this with an algorithm that keeps an internal state between queries. So for random quantum states, we achieve such a stateful simulation efficiently. And for random unitaries, we can at least prove that such a simulation is possible in polynomial space. Finally, as an application, we design a quantum money scheme that is unconditionally unforgeable and also untraceable. That's an additional privacy preservation property. To explain what I mean by stateful simulation, let's have a look at the example of a random function. So a random function from m bits to n bits is a very simple object, but exactly sampling it is infeasible as soon as the input length m is large. And therefore, there are several methods of simulating such a random function. So we study the oracle simulation problem. So we look at algorithms that have oracle access to such a random function, and we have a look, can we fool these algorithms into believing that they are interacting with an oracle for a random function instead of us who just simulate it. And for different limited scenarios, this is possible. For example, with t-wise independent functions, if the distinguisher is limited in the number of queries, or with pseudorandom functions, if the limiter is limited in runtime, if the distinguisher is limited in runtime. And the final line in this table is what the so-called lazy sampling technique. So here we don't have to put any limits, assume any limits on the distinguisher, but the simulation is stateful. This is a very simple thing. We just sample the outputs of f one output at a time. And whenever somebody asks the same question twice, we look up in a table which answer we gave last time. Now the question is first of all, just to illustrate the importance of these primitives or of these simulation methods, here are some applications in classical crypto. So these are really very important applications of these simulation methods. One interesting question is, of course, can we do the same thing quantumly? So for example, for a Haar random quantum state, so that's just a uniformly random state of n qubits. So we can maybe make a similar table. For example, exactly sampling it is completely infeasible because it requires an infinite amount of randomness. And also the other methods like the query limited case and the runtime limited case have been studied before. For example, by Jilu and Song, and also by Brakersky and Smurli. So they introduced pseudorandom quantum states. What we can supply now is the last row in this table, which is a stateful simulation method for random quantum states that works against any distinguisher. So we don't need to assume any limits on the distinguisher, but we pay for it by devising a quantum algorithm that keeps an internal state between answering queries. The same thing we can do for unitaries. There are two differences though. So first of all, pseudorandom unitaries have not been constructed yet, but that's none of our concern in this work. And we again can supply some form of the last row in this table, except that we only can prove that such a stateful simulation is possible in polynomial space. And we don't know anything about time complexity. Here's an example application. So one of the oldest ideas in quantum information processing is to basically construct money schemes from the no-cloning principle. And the most unclonable states are Haar random states in some sense. So one idea is for the bank to just sample a Haar random state and hand out copies of it as bills. And this is unforgeable and untraceable. This idea was put forward by Jilu and Song, and they instantiated it using their pseudorandom quantum states. What we can do now is we can instantiate this with the stateful simulation technique and thereby achieve unconditionally secure and untraceable quantum money. Here are some open questions. One question is, of course, can we simulate random unitaries efficiently? For now, we only know that we can do it in polynomial space. And one inherited question, of course, from Jilu and Song is, can we construct pseudorandom unitaries? So I consider this an important open question as well. This is the end of my talk. Here's a person performing lazy sampling, as you can see. Thank you very much for listening.
Good, thank you very much. So thank you to all the speakers, and we can open the floor now to the Q&A session. Okay, so feel free to, the panelists, you could share your questions on the chat to make sure it says your message will go to all panelists. The attendees, you could write your questions under the Q&A box. So there's one question there right now, and maybe I'll read this out, and you have some time to think about some more. So this question is to Jenna, and it goes as follows. In your first results slide, is the side information output Z classical? Is it okay to have it quantum? And V is a quantum verification procedure.
Yes, indeed. So V can be any quantum measurement with binary outcome. Z can be any quantum state, but it is essential that X is classical. Does that answer your question?
That's a question from Thomas Vidic, I should clarify. So Thomas is there. I don't know if you want to turn on your mic, Thomas, and add anything.
No, it's good, thanks.
Okay. We still have a couple more minutes. So we have a question from Niraj Kumar to Christian. Is there an intuition that random unitaries can be simulated efficiently by a BQP distinguisher?
Somehow, in my opinion, the intuition before our work was that neither of them can. Somehow because it seems like because you have these objects, like a quantum state, for example, is kind of a monolithic object. With a function, with a random function, you're just revealing one output at a time. But with a quantum state, in principle, you're giving out the whole thing at once. So it seemed impossible. But it turned out that that was not the case, because one can, instead of handing out a random quantum state, one can maintain entanglement between the simulation algorithm and the distinguisher. And in a similar way, I expect in principle the case of random unitaries also to be possible. It's kind of a bit counterintuitive because it seems like I would have to look at the query. But in some sense, I'm also allowed to do that because I'm destroying most of the information by applying a random unitary. So I think these two intuitions kind of counteract, and I'm not completely sure because I haven't proven it, but I expect it to be possible.
Niraj, did you want to add anything else? I think you're also able to speak now.
Yeah, it's good. Yeah, thanks.
Good, thank you. Ernest, it looks like you're there. Did you want to ask the question directly?
Okay, hello. This question is directed to Christian Majans. And this is regarding the full talk. Just perhaps a very basic question, but in the description of the simulator, you store the purifications of the previously generated states in the simulator, and you apply an isometry that extends them each time it's queried. Am I understanding that correctly?
That's right.
So why is it necessary to do this extension each time rather than just generating a fresh maximally entangled state, which seems informally that it would be Haar random on the reduced states?
So what your suggestion would indeed work if I was giving out independent Haar random states. But the goal is to simulate an oracle that samples a Haar random state once and then hands out copies of it. And therefore,
okay,
yes. So what the distinguisher sees is kind of the normalized projector onto the symmetric subspace, and then you indeed have to, if you hold a purification of that state, you need to actually extend it to the purification of a bigger projector, the projector onto a symmetric subspace of one more copy.
I see. And the stateless simulator example that you gave, the main problem that occurs there it's because the discretization just doesn't work somehow in this picture. Huh?
So somehow, I think why statefulness is required is kind of that we want simulation against arbitrary distinguishers. In particular, they are not query limited. We want that we remain efficient in the number of queries, but we don't know that number. So somehow, whenever you do a stateless simulation, you need to choose somehow an accuracy or something that determines the maximal number of queries, and that then you're already doomed.
I see. Okay, thank you.
Great. Or you've written a question. Did you want to ask Chris directly?
Sure. Okay, so I guess one of the advantages of state designs is that if you pick one of the states at random, say it's defined by some classical key K, you could give it also to others, and they could also generate the state as well, right? It doesn't need to be it doesn't need to be generated by the same entity. And once you have a state, this becomes more complicated. And I'm wondering if this is possible via some mechanism without communicating, right? That two people could, say, generate these Haar random states and keep their own state so that globally it looks like it has the same properties as a quantum T design. Did that make sense?
I don't think that should be possible somehow.
So that's also would be nice. So you're saying maybe it can be proved to be impossible.
I think it should be possible. It should be we should be able to prove that it's impossible. Yes, because somehow in some sense, to extend this, somehow my suspicion is that our simulation method, at least the blueprint, the blueprint of keeping a purification of the mixed state that the distinguisher sees, that this is kind of that this is kind of the only method. This is my intuition, and if that's true, then I think it's impossible, because extending this purification is actually acts on all the copies.
Okay.
Okay.
So in some sense, if one side hands out a couple of copies somehow, or applies that operation that corresponds to handing out a number of copies, then somehow the other side would have to act on their internal state to actually generate more copies. That's the intuition.
Okay, thanks.
Okay, so I see a question here in the Q&A box from Devdut Sharma. It's not entirely clear that this is the right session. Did you want to, Devdut, speak yourself, or I'm not sure if this is an accidental poster.
Yes, sir.
Yeah.
So,
did you wish to ask
I
your
came
question?
to know that yes. Question is, there is no strict rigid boundary between classical and quantum behavior of particle, and especially I am talking about nonlinear Kerr cavity medium nonlinear Kerr cavity, in which we realize the quantum state, but we using generally the photon for light reflection, but very macro, very weighted large glass sometimes show quantum behavior. I came to know only one or two paper in a conference regarding this. Means, is there any strict rigid boundary between quantum and classical?
Sorry, is your question directed at one of the speakers?
Means, in a nonlinear cavity research, quantum cavity, microwave cavity,
Yeah.
when we use the macro reflection glass.
Yeah.
I suggest we address this in the meet and greet room, which would be held after the session ends. Okay.
Yeah.
Dev. Yes.
Good.
We have 1 minute left. I'm just going to ask Omri a very quick question. So you said at the very end, so I'll wait till you switch on your mic. You said at the end that you didn't have time to get into techniques. You have 1 minute. Can you get into techniques? Well, what's the basic idea? How do you do simulation?
What's the basic idea in 1 minute? The basic idea in 1 minute is to homomorphically, okay. So the most like the super oversimplification is that the way that the simulator uses the fact that it has the circuit rather than only having Oracle access to this verifier circuit is that it's going to use it and perform quantum fully homomorphic evaluation when the circuit evaluated is the circuit of the verifier. When you do it like this, you can make, when you have this ability, you can make the verifier give you a secret that it doesn't want to give you, like in a supernatural. Yes, because in the interaction, it sends this secret. It sends you a challenge, and if you answer the challenge, then it answers with the reward, which is the secret. And when you use fully homomorphic encryption, you have access to the circuit under the encryption, and under the encryption, it gets the correct secret and gives you the reward, everything under the FHE, and you know how to use this encryption of the the secret in some additional way. Yeah. If it's I don't know if it made sense, but
yeah. So yeah, but it's still I give you pretty harsh constraints. Okay, good.